Okay, we are recording, and what I'm going to do is muck around with the moment generating function of the binomial distribution with Sage, which is a symbolic mathematical calculator. And hopefully, what I'm going to do is show you how to use moment generating functions, but without all the rubbish about differentiating and integrating and all the algebraic stuff. What we're going to do is get the computer to do the donkey work of differentiating and all that stuff, and we'll just see what happens. We're just going to see what happens. So I'm just going to remind myself what the binomial distribution, I'm just going to remind myself what the moment generating function of the binomial is. Here it is. Right, where am I looking? I am looking here. There it is, the moment generating function. 1 minus p plus pe to the t to the power n. I guess I could derive that in Sage as well, but we'll just take that for granted. Maybe I'll derive it later. I'm not sure if I can do that quickly. Right, so here's Sage. It's just a nice little symbolic calculator. So if I type something like 1 plus t to the power 7, let's just say, it gives me that. And I can do things like expand it, .expand. Maybe I've got to put this in brackets as well. I think this will work. Brilliant, there it is, so it expands it, and I can do things like, let's try 1 plus t cubed to the power 7, and I can do stuff like differentiate it, differentiate with respect to t, and do it twice, let's say, just for the hell of it, and it gives me this stuff here. So there you go, it does the hard work for us. So what I'm going to do is to define the moment generating function. No, I'm not. It's going to be a function of, what was it? Can't remember now. Here it is. It is 1 minus p plus pe to the t to the power n. So what variables do I need? I need little p, I need a little lowercase t, and I'm going to call it a large n, a capital N, because I'm going to need little n for something else. Moment generating function of p, t, and capital N. Here it is, bonk. And I want it to return, it's just a little function, 1 minus p plus exp, oh no, it's p times that, p times exp of t, all to the power of capital N. There you go. So now if I just type MGF of pt capital N, it just gives me that, which it's reordered. It's reordered that it's not 1 minus p, it's put the 1 at the end. But now I can be a bit clever and put 3 there, and you see it just takes that 3 and puts it there, because that's n, that's the power n there. So it's quite nice. So what I can do is take MGF of pt capital N, and I can differentiate it with respect to t. Well, let's just do it once. There you go, and it does it all at once. And now what we can do is the last bit, which is to substitute, I think it's subst, t equals 0, because that's what you have to do to get the expectation. NP, we knew that. That's the expectation of the binomial distribution. But I can be a bit cleverer than that. Look, watch. I can differentiate it twice and then substitute 0. Oops. Bonk. There we go. How about that? Well, I can even be a bit cleverer than that. I can say the expectation of x to the power little n. I can define a function for that. Define that is a function of little n, which returns the moment generating function of p t capital N diff t little n times. I said I'd need that. So we're going to differentiate it n times, and then we're going to do substitute subs t equals 0. How about that? So we've got this function here, exn, which basically returns the expectation of x to the power n, because the expectation of x to the power n is the result of differentiating the moment generating function n times, which is this bit. That's the moment generating function highlighted. This bit means differentiate with respect to t at would differentiate with respect to t n times. And this bit here means substitute t equals 0. So we're doing it all in one kind of big, oh dear. It's because I need def, not define. Blop, blop, blop. Try that. Fantastic. Now, we can just try that. exn of 1 means the expected value of x to the power 1. Let's try that. np, check. Let's have a look at 2. Well, we did that up here, didn't we? So that checks. But now watch. 5. There you go. It's a mess. It's a mess, but there it is. Actually, I can do a little bit better than that. I can do dot full simplify, which does a bit of algebraic simplification. Oh, well, it hasn't done anything there. Look how complicated this is. Look how complicated this is. Now, what I want you to observe here is that, look, we're working out the expectation of x to the power 5, where x is distributed as binomial np. So that's what this thing here is. But look, it's basically n to the 5, p to the 5, so it's np to the power 5, minus some stuff, plus some other stuff, minus this, plus that. But the leading order term, the most important one, is this. And these, I guess, are just corrections. These are just corrections. Okay, so how can we use that? Well, what do we want to do? Well, I'll tell you what we'll do. We'll verify it. It's already longer than I wanted. I'm going to stop here and I'll verify it on the next screencast. Okay, I'm stopping here. But the next one, I'm going to verify it.